Thanks for joining us today to learn more about the Trimble Alloy GNSS receiver. This is the third in a webinar series that goes into more detail about the functionality of Trimble's new Alloy reference receiver and what sets it apart from previous reference receivers. Alloy is Trimble's flagship reference receiver, introduced in January of 2018, and we are continuing to hear from users about how easy it is to set up, use, and the quality data they're receiving from it. As a reminder, if you haven't already seen the previous webinars in this series, here's a quick overview of what Alloy is about. So it's our next generation hardware architecture. So it's very powerful performance we have in this receiver, most powerful receiver in the market today. It's got the latest GNSS technology, capable of tracking all the signals that are available today and in the near future. As you can see, it's got a new design that makes it very easy to use, and it's also designed for rugged environments. It's got a rugged design for very harsh environments. Quick overview of who you'll be hearing from today. My name is Kent Enkel, and I will be facilitating this webinar. And because we respect your time, we're going to be keeping this to right at about 40 minutes. The main presenter for today is going to be John Serink. He's a global technical sales engineer at Trimble, who's been consulting and installing GNSS systems for Trimble for over 20 years in countries around the world. He'll share some of his broad technical knowledge on how Alloy features can help you set up, maintain, or upgrade your core site. And with that, I'll pass it over to John.
Okay, so for our agenda for today is we're just going to go through a bit of the new features of firmware 5.37 for Alloy that just came live last week. Those two features that we're going to go over are the Beidou Generation 3 SV support for Alloy and the new anti-spoofing features. And after we talk about those for about 5-10 minutes, maybe maximum, we'll get right into the Spectrum Analyzer, which I think is mostly what people wanted to see today anyway. Okay. So I think most of our users would already know about this. Alloy is brand new. It's been designed to be able to receive anything that's expected to be put up in the next 5 to 10 years. Currently, it can receive every satellite that's currently deployed now. You'll see some screenshots of that in a few minutes. From the unit that I have deployed in Singapore. But from what we know today, this is what we foresee happening up to 2021, and Alloy is more than capable of covering all of this and then some. So we're looking forward to more signals, more satellites, and maybe a few more countries will put some stuff up. Who knows? Okay. This is a little screen snap of my receiver in Singapore, just to let you know that I was using 5.37 when I was doing the testing. So okay. Okay, here we have the satellite tracking table for Beidou, and you can see that. B3, B1, and B2 are all coming in, and we know for sure that SVs 26 through 37 and 19 through 22 are the Generation 3 satellites, and those are coming in fine. We've got 4 satellites that are still unhealthy, which is to be expected. Those are new ones, so those are still being worked on. Okay. So this is the sky plot from my unit in Singapore. And typically with a 5-degree elevation mask, I will be receiving between 40 and 48 satellites. If I drop the mask to 2 degrees, I'll have up to 60, 65 satellites in view at any one time, receiving 40 to 45. We get so many in Singapore, obviously, because it's only 1 degree north of the equator, so we have absolutely fantastic coverage. We also are able to pick up the IRNSS geosynchronous satellites and the Beidou geosynchronous satellites as well, due to our geography. Okay. Now, firmware 5.37 contains some really interesting new anti-spoofing code. And to understand what it's doing, we should first define what spoofing is. Now, spoofing is the intentional manipulation of GNSS signals such that the associated GNSS receiver computes an incorrect position. So essentially, it's someone that's sending out false satellite signals to trick your receiver into computing a solution other than where it actually is. Now, at one time, spoofing was the domain of state-sponsored actors only, but no more. Okay. Now, I think everyone's heard of Pokémon Go before. This is a cell phone application game that combines maps of where you are into hunting down little characters on the screen. Now, a bunch of people wanted to go hunt Pokemons in Japan without having to actually get on an airplane and fly to Japan. So they figured out a way how to spoof the GNSS receiver inside their cell phone. And this is an open source set of code. You can go download it. There's the link on top. And yeah, this stuff is just, it's all out there. So if they can fool your phone, they can fool your GPS receiver or your cores. Okay. This little bit of kit that you see in front, this stuff was on the tables at DEF CON last year. And you could pick it up for $500. What you've got there is a Raspberry Pi computer connected to a little RF GNSS spoofer. So you can drive this thing from this little Linux computer and have your own little spoofer. And this thing is $500. So it's something that is no longer requires a state-sponsored level of sophistication. You can pick this stuff up all over the place. You can download the code. So this is an issue that we're going to have to start dealing with more and more. Okay. Now these are some anti-spoofing results that we picked up when Trimble was working with DHS last year. We recorded all of the data, the spoofing data that DHS sent out while we were at their test range, and we brought that back to the lab, and we used it as a test base to develop firmware 5.37. So what you're looking at, the blue bars there is firmware 5.33, and the orange bars is firmware 5.37. And you can see that the orange bars are much more resistant to the spoofing than the blue bars were. You can see on the first test one, for example, unbelievable as it may seem, the GPS receiver was producing a position that was 100,000 meters away from where we actually were using firmware 533. 537 pulled that spoofing result down to 45 meters. So not perfect, but a vast improvement from 100,000 meters. Test 2 was 5,000 meters out. With the anti-spoofing code, it brought it down to 40 meters. And you can see the other results are quite similar. So quite dramatic improvements. Okay. Oh, one thing I should mention about the spoofing. To make use of it on firmware 537, you have to enable the Kalman filtering. Some cores operators don't want to do that. It's a decision you'll have to make. Yeah, to get the anti-spoofing functionality, you'll need to enable the Kalman filtering. Okay. Now we're going to talk about the Spectrum Analyzer. Now I realize most of the people that are on this webinar are probably from the civil engineering and surveying or geophysical background, so you won't have a lot of experience with what a spectrum analyzer is. So first we're going to go over what the device is. It's a piece of test equipment that works very similar to how an oscilloscope works. Now an oscilloscope, you can see on the diagram here on the left, shows a signal, and it has the amplitude on the y-axis, and on the x-axis it displays time. The spectrum analyzer does almost exactly the same thing. On the y-axis, it also displays amplitude, but on the x-axis, it displays frequency, not time. So it allows you to resolve different frequency components in a signal. Now, if you look at the diagram, you'll see that on the oscilloscope, you get a composite signal in time, whereby all those sine waves are added together. And you look at that in the time domain, and you can't really make out what that waveform is made out of. But if you look at it on the spectrum analyzer, it becomes very clear that you have three signals you're looking at. So that's where the spectrum analyzer comes into its own as a piece of test equipment. Okay. Now, when you go into the spectrum analyzer display on Alloy, if you need more information, you can just click on that little question mark there, and as long as your Alloy is connected to a network drop that has internet access, the help will come up in a different window, and it'll be the help for the spectrum analyzer, and you can access all the information right there. If you want to get the help offline, you can go over to www.alloy.trimble.com. That'll take you to the help files. You can navigate to the help files that are on the receiver, or you can download a zipped file of those help files. It's all there at that www.alloy.trimble.com. So there's more information there if you'd like to have it locally or just see it online. Okay. So you got your Alloy, you got your spectrum analyzer set up. So what do you do first? Well, one of the things that you should always do is you need to convince yourself that what you're seeing on the screen is actually what's there. Now, I don't know if any of you have ever watched an electrician, an electrical contractor perhaps that you've called into your home to fix something. If they take a meter out, the first thing they'll do with their DVM before they measure any voltage is they'll touch the probes together. And the reason they do that is to make sure that the screen reads 0. They're in effect calibrating their machine before they use it. So we're going to do sort of the same thing with the spectrum analyzer. We are going to convince ourselves that the thing is actually working and picking signals up from where our antenna is located. And what we're going to do is read a signal that we know is out there. So the question is, where are we going to find this signal? Well, your local airport. And we're going to show you how to do that. But first, we're going to go through a few of the displays available on the Alloy Spectrum Analyzer. Okay. Now, there are two display types available. One is the Spectrum Analyzer display, which is the one everyone sort of is used to and expects. That's the one that's on the top. Okay, it's got some really neat features. You can just float your mouse cursor over top of that display, and it'll show you, and the cursor will drag along the signal line, and it'll show you the frequency and the relative amplitude of that signal where the cursor is. That'll show up in that little gray box in the top left-hand corner. Now, if you click on the little history display, it'll change to the display that's on the bottom, and that's what we call a waterfall chart. So on this chart, time is on the left, is on the y-axis. Frequency is still on the x-axis. And now we can see the signals based on their color. Their amplitude is shown in color. So no signal is a darker color. Signals that are light in color up to red. Red is a very high signal level, and a lighter color is a little bit lower. But this is useful to see time series. So if you have a signal that shows up and disappears and shows up and disappears, you can see it on the waterfall chart. So it does have its uses. It's very interesting. Now you can observe 7 different bands. All of the GPS bands, the Galileo bands, and the BeiDou bands are all available, plus the MSS band, which is what RTX uses to download the corrections for RTX. There is some overlap, but let's have a look at those displays now. Okay. All right, so there's your L1 display. Notice that there are 3 filtering modes. Right now, the display that you're seeing is in the default, which is the filtered spectrum mode. That cleans up a lot of the noise and gives you something you can look at and read very easily. Max hold is a type of display that you would use if you're trying to look for a signal that is very sporadic. The thing about the filtered spectrum is that it integrates everything that comes into it, so that if you have something that's only showing up every couple of seconds, it might get integrated out, whereas if you switch to max hold, you might be able to see it better. The no filtering spectrum is very hard for unexperienced users to decode. It looks basically like an oscilloscope noise signal, but if you're trying to catch a transient type of signal, that's where you'd like to go. Okay, let's go to the next one. And the next one shows us our L2 bands. And you can also see the visualization option there. Show center frequencies. If you click, you can see that it's enabled right now. That just puts a line where the center frequency of the band of signals for a certain satellite constellation should exist. If you untick that box, those lines will disappear. I always leave them there because I like to know where the satellite signal should be. You'll also notice that you can't see the satellite signals. This confuses a lot of people, but that's normal. GNSS signals at the Earth's surface are about minus 160 dBW in amplitude. That translates to 1 times 10 to the minus 16 watts. And that's well below the noise floor of the spectrum analyzer. And the satellite signals are designed to be that low. Okay, so they're below the noise floor. That's why you can't see them on the spectrum analyzer display. Okay, let's go to L5. And there's what L5 looks like. Let's go to E6. And B1. And S1. Now, notice the frequency band on S1. That's up around the ISM lower 2.4 gigahertz band for Wi-Fi. What you're seeing here is pure noise, because although Alloy can receive these signals, the Zephyr 3 antenna to which this particular Alloy is connected to can't. So there's nothing actually coming into the antenna on this frequency band, even though Alloy could decode them if the signals were there. So what you're seeing there is simply the noise floor of the receiver. Okay, and over to MSS. Now this signal you can see, because this is a narrow band communications signal. It's a low bandwidth communication signal. It transmits the RTX corrections, but you can actually see this one. And that's what it looks like. All right, let's go to the next one. Okay, back to the airports. Where are we going to find a signal that we can look at? Well, everyone has an airport around where they are. And so we're going to use a little a navigational aid used by aircraft that's been around since the 1930s, and it's called the Vector Omni Range, a VOR for short. Now, the civilian version of a Vector Omni Range uses a VHF signal to give an azimuth from the VOR, and it uses a DME pulse to give the aircraft a distance, so you get a range and a bearing from the VOR. The military version of a VOR is called a TACAN, which works exactly the same except it uses a UHF sweep. But the TACAN uses exactly the same frequencies on the DME. So that's what we're going to be looking at, the DME frequency. That's what we want to see. Okay. Now, in Singapore, this is an example of the airports that we have around. Okay. So you can see there's a couple of military air bases and a few civilian ones. Okay. This is a table of the available NavAids. NDBs are at 300 kilohertz, so that's not going to be of any use to us. What we're looking for are the TACANs and the VORs. Now, you see the channel numbers. Those things can be looked up to decode what the DME frequencies are, and we've done that on the next slide. Okay. And here we are. The Paya-Lebar TACAN, because Paya-Lebar is an Air Force base, so it's got a military version. It's on channel 110X, and that translates to a DME frequency of 1197 megahertz. Papa Uniform VOR is a civilian. It's at 98X, and it's at 1185 megahertz. St. John's Island is a VOR. It's on channel 82X, and it's on 1169. That's actually quite close to our office, probably about 8 kilometers away. The Tenga TACAN, again, is an Air Force base. 086 is the channel, and it's on 1173. And Tekong, another civilian VOR, is at 112X, which is at 1199 megahertz. Okay, let's go have a look at Alloy and see if we can see any of these. And sure enough, on the left, I'm not sure if you can read that little gray box, but it says 1169.077 megahertz, and you can see there's a pulse sticking out right there, and that's the St. John's Island VOR DME pulse. Okay, and if you look over on the right, you can see the same signal using the waterfall display. And you can see that the DME pulse at 1169 megahertz shows up as a green line, which means it's pretty steady and it's there all the time. Let's go to the next one and see what we can see. Okay, this is Tekong's VOR. It's farther from our office. It's about 25 kilometers away from our office. That's why it's so small as compared to the St. John's, but you can see it's still there. And again, it shows up on the waterfall chart as a lighter color than the St. John's VOR because it's smaller amplitude. So yeah, you can pick this stuff up. Now, wherever your Alloy is deployed, obviously you'll see different DME signals because you'll have different airports on different channels. But this is something really handy that you can use to convince yourself that the Spectrum Analyzer isn't putting some sort of JPEG up out of its memory just for show. It's actually picking up what's out there. Yeah, okay, so the summary. We've gone over the few features, a couple of the major features of the new firmware release, the 537 release, which is the Beidou Generation 3 SV support, and the anti-spoofing features. And we've gone over just a light glossing over of the Alloy Spectrum Analyzer and how you can convince yourself that it's actually working by picking up local airport signals on the L5 display. So that's all we were meaning to cover on this little webinar.
Okay, great. Again, I wanted to thank everyone for joining. I want to give a special thanks to John. If you've looked at your world clock, it's not exactly working hours in Singapore. So John, thanks so much for joining us.
Not a
Thanks
problem.
for all of our, thank you so much, John. And also thanks for all of the participants. We appreciate you joining our webinar and learning more about Trimble and our Alloy receiver. Thanks, and have a great day or great evening, depending on where you are in the world. Bye-bye.